Is dark energy actually light? Quantum physics may have the answer. In November 2020, Cramer, the president and CEO of Hyperstealth Biotechnology Corporation and holder of 40 patents in the field of physics, including a light-bending invisibility material, proposed a new theory about dark energy that light itself was the perpetrator for the acceleration of the universe's expansion and not some unknown, undiscovered particle or particles. Recent data from the James Webb and Hubble Space Telescopes may help to confirm his theory. These two space telescopes have discovered something baffling to astronomers and created one of the biggest problems in all of physics. The universe appears to be expanding at very different speeds in different parts of the universe, crushing their leading theories for dark energy. The irony here is that the Hubble Space Telescope is named after Edwin Hubble, who in 1929 discovered that galaxies were moving away from us in all directions, proving that Einstein's theory of a static universe was incorrect. Both Hubble and Einstein knew the implications of an expanding universe. This meant it had a beginning, which we now refer to as the Big Bang Theory. About 68% to 70% of our universe is something called dark energy. Normal matter accounts for close to 5% of the universe, and dark matter is believed to be the remaining 24 to 27%. Dark energy, like dark matter, is named dark, not to signify that it's dark, but that it is unknown. No one knows what dark energy is, but we know from recent observations of the universe that about 5 billion years ago it began accelerating, not slowing down as expected, and has been accelerating faster each day. Dark matter was the dominant force in the universe for the first 9 billion years, with a strong gravitational attraction. Now, dark energy with a repulsive force has become the dominant force and is growing stronger every day. However, it's not happening at the same rate throughout the universe. This problem, known as the Hubble Tension, has the potential to alter or even upend cosmology altogether. In 2019, the Hubble Space Telescope confirmed the Hubble Tension was real. In 2023, the James Webb Space Telescope made even more precise measurements to solidify the discrepancy. A study released in February 2024 verified that there are no measurement errors between the two space telescopes. The differences in speed measurements are considered a crisis, according to David Gross, a Nobel Prize-winning astronomer. So how does Cramer's theory solve this dilemma? Quantum mechanics and the wave-particle duality of light. Light can behave like a wave and a particle at the same time, as the double-slit experiment demonstrates. When coherent light has to go through two slits at the same time, we don't see two bands of light on the opposite wall as one would expect. We see multiple bands of light because the light particles are also acting like waves which interfere with each other, like dropping two pebbles in the same water source. The ripples will interfere with each other, causing some to increase in strength and other to decrease or cancel out. Cramer has seen this firsthand using a laser with a lenticular lens to split a laser, the basis for his patent, which has recently been granted in 4 countries with a 5th approved but not yet granted. When the laser is aimed at an angle to the lenticular lens, an interference pattern appears which indicates light waves interfering with each other. This is like the double-slit experiment, but on a massive scale with hundreds, thousands, or millions of lasers interacting with each other. Guy explains, "When I first noticed the interference pattern, I immediately thought quantum mechanics was occurring. Experts in optics have since verified my assumption as 100% accurate. This means photons of light do influence other photons, even at large scale." Another recent study has shown that 2 light pulses emitted in parallel in the same direction do not attract or repel each other, but if light pulses are emitted at 2 different sides where they are opposed to each other, they will gravitationally attract the other as they pass close by. The most interesting aspect observed is that there is a gravitational component to light, but only during emission and absorption, with emission being an attractive force and absorption being the opposite repulsive force. The research is also applicable to gravity waves from cosmic sources. Quantum field theory calculates a value for dark energy that is 10 to the power of 120 times larger than what is observed. If that number was correct, space would be expanding so fast that stars and galaxies could not form. In other words, they don't know what it is. The early universe lacked light. As dark matter coalesced, it attracted hydrogen, which compressed under this gravity to form the first stars. New stars continued to form faster, often from the remnants of dead stars or supernovas producing heavier elements, until star formation peaked 10 billion years ago. Stars can emit light for many millions or billions of years, depending on their size, color, and temperature, with larger stars burning faster and brighter. The most dominant stars in the universe are small red dwarf stars, and these may burn for trillions of years. However, they are quite dim as they are structured to conserve their energy output, leading to their ultra-long lifespans. Cramer postulates, if light has an attractive gravitational effect at its source of emission and a repulsive gravitational effect when absorbed, would those photons, which peaked 10 billion years ago, eventually have achieved enough light absorbed or repelled to cause a repulsive gravitational effect to overcome the combined gravity of matter and dark matter and accelerate the expansion of the universe? Or could it simply be that photons of light are being repelled by photons of light heading in the opposite direction, and that repulsion is transferred into energy, which hit the tipping point 5 billion years ago to accelerate the universe? Directly or indirectly, light could be the engine that powers dark energy. It fits many of the fundamental aspects surrounding the mystery, an energy that was minimal or non-existent during the early dark age of the universe before stars could form. An energy that seemed to grow in strength as the universe aged, overtaking the gravitational attraction of the universe about 5 billion years ago with a repulsive force. The speed of light is limited, and if star formation peaked 10 billion years ago, the spread of photons building to that point would take hundreds of millions of years to cross a void before they were absorbed by dark matter or matter within a filament, and their energy became repulsive or interacted with that matter to create quantum particles with a repulsive force or a negative mass. Only a small percentage of the photons would hit the closest filament, and most would travel hundreds of millions or even billions of light years further before an interaction with matter occurred. Star formation has not stopped, just slowed down, and while we may have less photons being produced today, there are still photons moving through space at the speed of light that were produced near the beginning of the universe, after the Dark Age, that we detect on telescopes today. Cosmologists have calculated the amount of visible light released by stars into the universe, since the universe's origin is 4 times 10 to the power of 84 photons. This number is a 4 with 84 zeros after it. Recently, starlight and galactic gases have been observed to have polarizations that far exceed current models, which could hint at a photon versus matter interaction. Photons will continue to move until they run into something, and while the absorption may not seem like it could impart much of a repulsive force, photons are being produced every second from numerous sources, including stars within more than the estimated 2 trillion galaxies that exist. Is it simply light going in one direction interacting with light going in the opposite direction? Is light somehow converting to highly repulsive polaritons or other quantum-like particles when it finally interacts with matter or dark matter through a means we don't understand? Cramer says this repulsion of light photons to other photons or photons being absorbed by matter would not be uniform across the universe. There would be places where greater star formation took place, which in turn billions of years later should result in a higher expansion speed, versus regions with less star formation, which should result in slower expansion rates, as shown in the Hubble tension. Guy uses the analogy of expanding bubbles of photons emitting outward from each light source, which push against opposing bubbles of photons from neighboring stars and galaxies, which are also expanding, thereby inflating the universe faster and faster than if no interaction took place. Guy concluded that his experiment, which demonstrates that light even at large scales has interference patterns due to quantum mechanics, could mean that the interaction of photons to opposing photons in the universe could be dark energy. It's just happening at the quantum level. On a final note, if light photons didn't repel each other, those lightsaber fights in Star Wars would be over quickly, as you couldn't defend against the other saber. The sabers would just go right through each other.